To give you an example, what is called in mathematics concrete example, mathematicians use many terms in a very perverse way, in particular the word concrete. It is of course not concrete in any sense in which we use this word in common language. It's concrete in this sense that we don't deal there with arbitrary operations satisfying certain conditions, but in operations of a well-defined set theoretical character. So let's consider an arbitrary set A, of which we assume that it is not empty. By a binary relation on a binary relation R on A, we understand, in set theory normally, every set of ordered pairs. Everything which has a graph in a normal two-axial coordinate system, in case A is the set of real numbers. But, as I say, A can be a set of an arbitrary character. If, as it is normally done, by A cross A, we denote the Cartesian square of A. This means the set of all ordered pairs whose members are elements of A, then we can say that a binary relation R is an arbitrary subset of the Cartesian square. So we know what is a binary relation on a set A. Now we can perform on this relation various operations. Since, for instance, R and S, another relation, are sets, we can treat them as sets. We can perform on them Boolean operations, such we can take union of two relations, intersection or common part of two relations. Given any relation R, we can form the difference between A cross A and R, which we denote simply by, in this way, putting A here, and we call it the complement of R relatively to A. If A is fixed, we simply omit A here and here. So we have a unary operation on relations. Then we have also a certain operations on relations which do not apply to arbitrary sets, which are characteristic for relations, for binary relations, and have no clear meaning when applied to sets that are not relations. Such is the operation of relative product or composition of two relations, which we denote by means of straws, following Principia Mathematica. What do we understand by this? This again a certain set of ordered pairs. If I use normal set theoretical terminology, I could write here the set of pairs xy, where x and y belong to A. So as you see, this operation also depends on A. But A is assumed to be fixed. No? And let me use normal logical symbolism. There exists a G belonging to A, such that xg is in R and Gy is in S. So this is the relation the operation of relative multiplication of two relations. We know many examples of this operation. It's a very important operation, well, in common language even. And the evidence is provided by the fact that for the relations, for all the relative products of certain relations whose names exist in common language, special terms were introduced denoting this product. To give you an example, and most examples which are given in this connection are from the domain of family relations. Let's take the relation of being a son-in-law. So let T be the relation of being a son-in-law. If I write XY or XY belongs to T, I read this: X is a son-in-law of Y. And now what is the common definition of this relation is this: to say that X is a son-in-law of Y means that they exist as V, such that X is husband of V, and V is daughter of Y. So that T is defined in this way. T holds between X and Y if they is as V, so that X is husband of V and V is daughter of Y. Therefore, according to our definition, T is the direct product of H and V. Relation of being son-in-law is a direct product of the relation of being a husband and the relation of being a daughter. You can give many examples, as many as you wish. In particular, there are interesting cases when H and D is the same relation. This means cases when T is the direct product, relative product of two relations R, in this relative square of R, sometimes denoted in this way. For instance, if R is the relation of being a child, then R square is the relation of being a grandchild, because a grandchild means a child of a child. It is also a good field for exercises. For instance, you can ask the following question: is the relation of being a grandson a relative square of the relation of being a son? And then you see, of course, at once that the answer is, I expect you help and you don't give me. No. Because a son of a daughter is also a grandson. So you see, X is a grandson of Y doesn't imply that X is a son of G and G is a son of Y. Another example of a relation, of an operation of on relation, a much simpler example is the unary operation of forming a converse of a relation. Let me use here not the symbol converse, but the symbol more often used in mathematics, r to the power minus 1. The converse of a relation R. Well, this is the relation obtained from R by interchanging the terms in each pair. XY belongs to R minus 1 if and only if YX belongs to R. For instance, if R is the relation of being a child, then R minus 1 is the relation of being a parent. No. But if R is the relation of being a son, then R minus 1 is again not the relation of being a father, because it could be also that why we take not the father of X but the mother of X. And we